Okay, so the first couple we've done with e to the x and cosine, we're able to get kind of decently nice looking series. And it wasn't a terrible amount of work. This time we're going to have one that's a little bit more work for us to work out. And that is we're going to look for the Taylor series for ln of x around a equals 1. Now, we previously saw a power series involving ln, except it wasn't ln of x, it was ln of 1 minus x. That's where we had this series here, minus 1 minus times the series x to the k over k. Minus x squared over 2, minus x to the third, and so on forever. Right? And we, of course, based on some other results from earlier, knew when that converged. So that's one series. That series, though, was centered around 0, centered around x equals 0, because that originally had come from the series 1 over 1 minus x that we had integrated, because that was our geometric series. Okay, so this is a different center. This is a series with a different center. So it's going to look a little different. Should look somewhat similar, but still different because it is at a different center. So of course our functions are f of x equals ln of x. And we would evaluate that at our center. F of 1, of course, would be 0. And then we keep going with our derivatives. F prime of x would be 1 over x. F prime at 1 will be 1. We move on to f double prime of x would be the derivative of 1 over x. That would be minus 1 over x squared. And evaluate that at 1. We get a minus 1. And we keep going. F double prime be the derivative of that, so we're going to multiply by the minus 2. So it's going to be positive 2 over x cubed. And evaluate that at 1. And we're going to get 2. Triple prime. Right, we'll do multiplying by the minus 3, so that's going to make that a minus 6 over x to the 4th. Okay. And evaluating that at 1, of course, would give us a minus 6. Okay, and we keep going. Fourth derivative. We would end up multiplying by the minus 4, which would get us to 24. And the exponent would now become 5. So fourth derivative, evaluated at 1, would just be a positive 24. In general, what's going to keep happening here is I want you to notice a few things here to see what the pattern is. Right? And a minus 1, so we have an alternating sign first of all. Right? Alternating sign. On the even derivatives, the sign is positive. On the even derivatives, the sign is going to be, did I say this right? Make sure I'm not missing something here. Okay, I see I spotted a little place where I made a mistake here. That is actually the third derivative. This is the fourth derivative. So therefore we're on our fifth derivative there. So a little bit of a mistake there. Lost one of my primes and kind of messed things up there. So apologize there, but I'm glad I was able to catch it, because that makes a big difference. So let's look again at what we have here. So the first thing to note is that the odd derivatives have the positive sign, and the even derivatives, except for the first one, which doesn't matter because it's 0 anyway, are the ones that have the negative sign, the even derivatives. Okay. Second thing I want you to notice is look at these numerators here. We have a -1, then a 2, then a 6, and then a 24. The 2 is 2 times 1, or 2 factorial. 6 is 3 factorial. Then the next time we multiply by 4, which would make that 4 factorial. And then the final thing is the denominator. The exponent is actually just the derivative that we're taking. So in general, we can see this pattern, that the nth derivative of this thing will be a -1, and it's going to be to the n plus 1 power, because again, we want the odd terms to be positive and the even terms to be negative. And then the numerator is going to be the factorial that's 1 smaller than the derivative we're taking, because the next one we multiply by 5, the 6th derivative. So that's going to be n minus 1 factorial, and then that's all over x to the n, all over x to the n. So when we evaluate the nth derivative at 1, that's just going to be -1 to the n plus 1 times n minus 1 factorial. Okay, the denominator will just disappear. And so that's what my coefficients look like for the derivative part. And so with that all worked out now, we can finally put it together to start talking about our series. Right? The general series. Starting at k equals 0 to infinity, right, is the kth derivative, evaluated in this case at 1 over k factorial x minus 1 to the k. And then we just fill in our kth derivative. But we recognize one important thing, that the pattern that I've stated here only works in being 1 and larger, right? The first derivative doesn't follow this pattern. Or sorry, the original function doesn't follow this pattern. That turns 0. So when I write out the new sum, my sum is going to lose the 0 value. And we're going to start at 1. Then the rest of it just follows this pattern. So -1 to the k plus 1 times k minus 1 factorial, and then that's going to be over k factorial, and then x minus 1 to the k. And then we simplify, and we realize, well, we have a k minus 1 factorial on the top and a k factorial on the bottom, so everything goes away except for the k in the bottom. We'll get sum as k goes from 1 to infinity of -1 to the k plus 1 over k x minus 1 to the k. All right, so there's our series for the ln of x centered at 1. And just for reference, the first few terms, k equals 1, that's going to be a positive power, so that's actually just going to be x minus 1. K equals 2, that'll be a minus, so minus 1/2 x minus 1 squared. Of course, 3 will be plus, so it'll be plus 1/3 x minus 1 cubed, and then minus 1/4 x minus 1 to the 4th, and then plus, and it'll be 1/5 x minus 1 to the 5th, and so on and so on. Okay, and then we ask the question that we've asked before now that we've built the series. when does it converge? When does it converge? So we take the ratio of our coefficients inside the absolute value, and let's see what happens. Absolute value, k plus 1 term, so that'll be x minus 1, the k plus 1, over k plus 1 divided by x minus 1 to the k over k. And we simplify. X minus 1 to the k plus 1 over k plus 1 times k over x minus 1 to the k. And so all that happens here is the x minus 1 to the k is going to cancel with the kth power on top. Nothing else reduces there. So this is going to be absolute value of x minus 1 times k over k plus 1. Right. And then we take the limit of that as k goes to infinity. And of course, the limit of k over k plus 1 is just going to go to 1. So we're going to have absolute value of x minus 1. Right, remember that has to be less than 1 for it to converge. Less than 1 for it to converge. Okay, which means that x minus 1 will be between 1 and minus 1, which means that x will be between 0 and 2. Now, we still technically would want to check convergence at the endpoints because, again, it's not going to, remember the series convergence test here isn't going to tell us whether it converges at the endpoints or not. But here I'm just going to limit it to the interval here. But again, if we were testing general convergence, we really should go ahead and test the endpoints. And actually, why don't we just go ahead and do that real quick? So if we were plugging 0 in here, we're plugging 0 into our series. 0 minus 1 to the kth power would just be a minus 1 raised to the k power. And that's all that's going to happen when we plug 0 in is we're going to have a minus 1 to the k to join up with a minus 1 to the k plus 1. So again, at that point, you're going to have a minus 1 to the 2k plus 1 power when you put those together. But 2k plus 1 is always an odd number, so that's always just going to have a minus sign. So it's actually just going to be minus 1 over k. That's the coefficient. That's the series we're adding up. But we can factor the negative out and get negative of that series. But that's the harmonic series when we know it diverges. So at 0, it's not going to happen. At 2, we would have 2 minus 1 to the k, which would be 1 to the k, which would just evaporate. And so then we have the series minus 1 to the k plus 1 over k, which is an alternating series, and it does converge. So technically, we should go ahead and add on here that this does converge at 2. Okay. This does converge at 2.